have Z, okay? Now this is a lot to take in, but we'll apply it to something that happens all the time here on Earth, which is projectile motion, okay? So projectile motion is basically just the thing I was doing throwing the Post-it note. It happens in all sports. Anytime you throw a ball, anytime something flies through the air, it follows this basic projectile motion, okay? The key in projectile motion is in the x direction, we don't have any acceleration, but in the y direction, we have the acceleration due to gravity. And that always happens when, this is basically just free fall, but in 2 dimensions, okay? So projectile motion, remember, this doesn't include the part where this explodes. So when it's being accelerated through the cannon, that's not projectile motion. It starts as soon as you stop accelerating. So as soon as this cannonball leaves the end of the cannon, right, and is no longer being pushed by the explosion, it's under the influence of gravity and nothing else, okay? So remember, velocity vectors can be broken into horizontal and vertical components, meaning you can write an equation in x and you can write an equation for y. The equation for x should have x positions, right, and only x velocity components. So if you just get a velocity and you plug it in randomly, that doesn't work. In your x equations, you should have the x components. In your y equation, you should have the y components. All right. So here's our basic idea, right? This is our initial velocity. It's going to have an angle, right, theta from horizontal. So that means that velocity, that initial velocity, has an x and a y component, which you would use in the equation when you're figuring, in the kinematics equations when it looks for initial velocity. We also know that we only have acceleration in the y direction, and it would be the same for all of these. It's going to be negative g, okay? So if you want to write things out, we know we have to break up our velocity into x and y, and we also have to break up our acceleration into x and y, but that's a little bit easier, right? We don't have to do any trig to do that because we only have an acceleration in the y direction. Okay. So if we wanted to make these equations specific to projectile motion, we actually simplify them. Because what do? Well, we just plug in our velocities and our accelerations. So anytime we have an x velocity, we can plug in sine, or you can just leave it as vx and know that it's, cosine, right? And every time you have a g or an a, you can plug in 0, okay? So, and for y, you can plug in g. So it turns out, it turns out once you plug things in, these two end up being pretty much the same equation, and they're both kind of pointless because they just say that the velocity doesn't change. So you really end up, for projectile motion, you really only end up with 4 usable equations. You have all 3 of them for the y direction, but really only this for the x direction, because remember what this says is we have a constant velocity, okay? So we actually have this demo. Maybe I'll set it up next time. So here's a question. If you shoot directly at a coconut at the same time it starts to fall, do you hit it? So we have some yeses, some no's. So here's our trajectory without gravity. But what do we know gravity does to a trajectory? It's going to curve it down, right? And the difference between this line, because this is linear, so that would be v naught delta t, and this is just that term, 1/2 g t squared, okay? So it gets farther away over time, but it turns out that if you do this, they will still hit. Now, it's pretty hard to get a coconut to fall at the exact same time you fire a bullet, but they fall, we know just by watching the feather bowling ball thing that if they both start to fall, they should fall at the same rate, okay? And because they fall at the same rate, as long as they both start their fall at the same time, they should intersect. Yes?
Wouldn't it depend on the speed of the projectile?
It actually doesn't, because if it's faster, then it just hits the coconut closer to the start of its fall, but if it's slower, it hits it later. Because they're falling at the same rate, right? And because you've shot at the coconut, so its apex should be about the same as where the coconut is, they'll always intersect. So if you shoot a slow bullet or a fast bullet, it's just a matter of where in the vertical position that they intersect. And we actually have a demo for that, although it only shoots at 1 speed. And here's like a crappy video of it too. So here's a picture of the demo that a video of the demo that we had, where I think he's actually shooting a monkey, which is less cool, but it's a stuffed monkey, and so it didn't die. All right. We end up killing a lot of animals in physics. There's like the whole cat thing, and then now we're shooting monkeys. It's like it's not very. PETA's going to be after us. So, but yeah, you can also do the math on this. Does this look as bad to you as it does to me from up here? Is it like blurry? Cool. All right. We'll have to make our own. But I'll try to set that up for Thursday so you can actually see it in action in case. I know it's like a weird concept, but the key point here is, like we were talking about with the bowling balls and feathers, that things fall at the same rate. Okay? All right. Here's a question. I feel like maybe we'll do this again. Okay, take a minute. Huh. No one has changed their mind. Okay. Well, does it matter what the mass is?
No.
So you should expect the exact same behavior for both balls because the mass doesn't matter. So if the first ball landed 2 meters from the base of the table, where do you expect the second ball to land?
2 meters.
2 meters from the base of the table. Okay, so remember, mass doesn't matter. Okay. Don't think we have time to do this. We're going to end here for today, and then we'll finish this up on Thursday. So we'll finish this chapter up on Thursday. I also have the labs posted, so if you want to print them ahead of time, you can, but you can also print them in here. Over to the iPad so we can do it. But I would like you guys to start this problem. Give yourself about 5 minutes to try to do it. Set it up in the way that we set up homework problems, and then I'll walk around, make sure people are getting a good start, and then we'll do it together once we all feel like we've given it a good shot. Okay. Oh, and I'd also like to remind everyone, I know it's in the syllabus, but if you find mistakes in the lecture slides or the homework solutions or any of the content that's posted on campus, you get a point of extra credit that in whatever the related thing is where you found the mistake. I've already handed out like 3 extra credit points. It's good for you because you get extra credit. It's good for me because the next people that see the stuff don't have to see something that doesn't work. So.
Maybe, cause I think it could be free fall because it's like, you try, cause I think the question I say how far you try to land, but it's like he drives off with that 10 miles high, he drives off at 10 miles high cliff.
So it's free fall, right? But
Yeah.
he's going in the horizontal direction, so in the X direction. So he's going to continue traveling in the X direction when he falls.
Yeah.
Yeah. So you're going to figure out how far he lands from the base of the cliff.
Oh, okay.
So basically what you're doing is you're finding the time it takes to fall,
Mm-hmm.
and then plugging that into the constant velocity equation to get the X distance.
No, so, okay, so that's 0.
overthinking it already.
I specifically wrote this question to not have a calculation. Is that it? Oh, it's just. This car has to fall 10 meters. So you just calculate the time it takes to fall 10 meters, and you plug it into your x velocity, which is 20 meters. So we use an equation for that, right? We derived these last time. So we have delta y is equal to you can derive that. How are we doing? Anyone get any sort of answer? Do we want to work on it a little bit longer, or do we want to go over it?
Go over it.
Okay. All right. We'll set this up together. So let's start by reading the question, right? So we're going to look at what we need and what we have. We know we have a 10-meter high cliff.
Yeah.
So that's going to be what? How would you label that? Is that like X, Y?
Y.
Y, is it your initial or final position? Initial, right? So if you wanted to write that down, you'd say, okay, well, we know that Y initial is probably 10 meters. What would Y final be? 0, right? And that's sort of implied because you're going to be falling off a cliff. So you're probably done when you hit the ground, okay? The next thing we see is we have a speed of 20 meters per second. That's a velocity. Is it in the X or Y direction? X. So remember, let's say, what's X initial? What would we usually call that? 0, right? Because it doesn't give us a lot of information about it. We're going to be finding X final, right? That's our thing that it's asking for because it says, how far does the car land from the base of the cliff? That's X final, okay? We also know that this velocity, is that going to be in the X or the Y direction? I may have already asked that, but X. How do we know it's in the X direction? Yeah, because it's going off the cliff. We're assuming the cliff is flat. It obviously doesn't say that, but if it wasn't flat, it would probably give us some sort of angle. So we can assume that the car's driving along a flat surface and it just goes off. So it only has a velocity in the X direction, so we'll call that velocity initial X is 20 meters per second. What does that mean our velocity is for Y? 0, right? So that's going to be 0 meters per second, okay? We don't know anything about time, but this is all the information that we have. So what's the next thing we should probably do? Yeah, let's draw a picture. So here's our cliff, right? And it's 10 meters high. So we might want to draw our axes. Oops, oh, cool, I erased part of the cliff. So let's draw an axis. And I'm going to move that up. Oops. Okay, I'm going to turn the sound off here. Oh, this is very badly drawn. I'm going to redraw part of this. So here's our cliff. So we'll call this 0. We'll call this 10 meters, right? I'll move it over. Call this 10 meters. That means this whole thing, if we want to call this delta y, is equal to 10 meters. Or I guess it could be negative 10. It depends on how you're writing it, right? Because final minus initial. So delta y would be negative 10 meters. So remember, delta equals final position minus initial position. So this would be negative 10. There's a car, right? It's got an initial velocity of 20 meters per second. That's this, okay? And it's going to have a trajectory that looks something like this. Okay, so if we make our x-axis, whoops, oh, still blue. Cool, I have messed that up. The nice thing about editing later is I can get rid of all those mistakes. Okay, so this is x. This is y. They're all in meters. This is going to be our x final. That's what we're looking for, right? Because we want to know how far does this land, and so that's also this thing. All right. And we just have to figure out how to find that, okay? Do we want to make some estimates about what that's going to look like? What's a reasonable distance for this? So what's 20 meters per second in miles per hour, if you want to make a guess? What do we usually do for that? So it's not exact, but if you want to sort of estimate meters per second to miles per hour, you can just double it. So let's say we're going about 40 miles per hour and we drive off a cliff, okay? Hopefully you don't have personal experience with this, but what would be a good range? Like, do you think you could go a mile through the air? Probably not, right? So like in meters, something between 0 and 100, right? Maybe like between 10 and 100. Does that sound reasonable? So something between 10 to 100 meters. And we've sort of done this because we want to give ourselves an order of magnitude range. So that would be 10 to the 1 to 10 to the 2 is an order of magnitude range. So factors of 10. Okay? All right. Now that we have an estimate, what do we need? What equation do we need to start with? Because we have these kinematics equations, right? So we have the position one and then the velocity ones. We have them both for y and for x. So let's start with y, because if we look at what's happening here, what we really want to know is we know we can treat the motion in the x and y direction independently. So that means we need the time it takes for this thing to fall down, and we're going to use that time because we know there's a constant velocity in the x direction to figure out how far it's going to travel this way. Okay? Because no matter what's happening in the x direction, we know falling 10 meters is going to take the same amount of time no matter what. Okay? So we're going to start with this equation, which is y final is equal to y initial plus v naught y t plus 1/2 a t squared. And you could say delta t, but remember we know initial time we can just call 0. So I'm just going to write it this way to make it a little bit less messy. Okay? So this is our equation that we start with. This is our position equation, our kinematics equation for constant acceleration. All right, we can rewrite this using what we know. So what do we know about y final? Looking back at it's going to be 0. What about v initial in the y direction? Our initial velocity in the y direction?
0.
Also 0, right? Because we only have velocity in the x direction. So we're not, this equation has nothing to do with the x direction, so anything you have for the x direction, wait till the next equation, okay? So we know that. We also know that we can rewrite this as negative g. Okay, so then we'll rewrite this whole thing, and this is going to end up being 0 is equal to y initial minus 1/2 gt squared. Okay, so we can solve this for time. And why would we want to solve this for time? Well, first off, it's the only thing we don't have, okay, because we know y naught is 10, and we know what g is, that's 9.8 meters per second squared. But as we were talking about before, since x and y happen independently, the only thing that connects them is time. So if we can figure out the time it takes for the car to fall 10 meters, we know how much time we have for it to travel at a constant speed of 20 meters per second to the right, okay? So we'll write this out and we'll do some algebra. So this becomes t is equal to 2y over g square root. Okay, that's my fast, quick, dirty algebra that skips some steps. Okay, if you want to go through the steps, we can talk in office hours and I can walk you through those things. Okay, so now we plug in numbers. So that's going to be 2 times 10 meters over 9.8 meters per second squared. We plug all that in. We get a time of 1.43 seconds. So here's our first step in this problem. Okay? Now what are we going to do with this time? What does this time tell us? Yeah, it's how long it takes to fall. And so that's just in the y direction. Now we can go to the x direction and we can use a different equation. What's the equation we want to use for the x direction? Yeah, now we have velocity and time. And so we know in the x direction, velocity initial x is going to just be delta x over delta t, okay? Which in this case is just because initial x is 0 and initial t is 0, just gives us x final over the time we got, okay? So we can write this out as x final is equal to v initial x times t. Well, we just found t, and we also know that v initial x is 20 meters per second. So we just plug this in, and that's going to give us 28.6 meters. So x final is 28.6 meters. Okay, so a couple questions. Does this work with what we estimated?
Yes.
Yeah, this is between 10 and 100 meters. So it's going to be on a cliff, the height of like 33 feet, that's 10 meters. It goes 40 miles an hour off that cliff, and it travels about 29 meters, okay? Which should make some physical sense if you've seen a movie where something drives off a cliff. Do not try this at home. So it matches with our estimate. We've used our kinematics equations, and the key here is whenever you're doing projectile motion, you want to treat the x and y motion separately. So going back to what we did at the beginning, we found out our values, so our position and our velocities in terms of x and y. Now, how could this problem be trickier? What's something we could do with the initial velocity that would make this harder?
Going down a hill?
Yeah, it could be going down a hill and then falling off the cliff, right? So then it would have some initial velocity in the negative y direction. It could be going off a ramp, right? So then it would have some initial velocity in the y direction up. So you'll notice here, for this equation, what happens if you have an initial velocity in the y direction? Like, what horrible math occurs then?
Quadratic formula?
Yeah, so if you can't make this term go away, you end up having to solve a quadratic equation, which is not the end of the world, but does add a little bit more trickiness to the algebra of the problem, okay? So this is a very simple version of this problem, but you can make it a lot more complicated by just adding a velocity in the y direction, okay? And this is something we're going to do in the lab. We're going to shoot metal balls at stuff in the lab, and that will include something in the y direction, okay? Cool. So our numbers seem reasonable. We're feeling good about this problem. Here's a secondary thing. A lot of times in high school, they teach you about the range equation. The range equation is really just a solution to the same kinematics equations that we did, but you're assuming that your y initial and final positions are the same, and then you just do some algebra. Okay, so you solve for the time, you plug it into x, then you find the range. It's basically what we just did, but you can't have y's at different heights. So that's a very specific case. We don't necessarily do that because it's easy enough for you guys to solve for it if you want to. But the key of the range equation is if you solve it and you want to figure out the maximum distance, how do we find a maximum in physics? What math thing do we have to do for maximums and minimums? Take a derivative, okay? So if you take a derivative to maximize x, so that you take a derivative with respect to theta, right? Because you're going to end up with theta for the angle. You find that the maximum angle for everything is what? 45, right? So if you shoot things at 45 and they're landing at the same height that they left the ground, that's always going to give you the maximum x distance. And there's a way to think about this that's pretty intuitive, right? If you shoot something straight up, it doesn't travel very far in the x direction. If you shoot something straight out, it doesn't have very much time to fall before it hits the ground, okay? Because it's already too close to the ground. So what you're doing is you're maximizing the amount of time it's in the air by giving it both an upward velocity, but not so much upward velocity that it just goes way up and comes straight down. Okay, and here's like basically an animation that shows what this looks like, but from a height. So this is our maximum range. So these are just different trajectories if you drive off a cliff at 200 meters at different angles. Okay, cool. This is something you can do in MATLAB if you're feeling very fancy. Okay, I think you can also do it in Python.